Today we're going to be looking at the 2025 Putnam A1. And so we're given m0 and n0 to be distinct positive integers. And for every k thereafter, we define m sub k and n sub k to be the relatively prime positive integers such that m sub k over n sub k is equal to 2 times n sub k minus 1 plus 1, that entire quantity all over 2 times n sub k minus 1 plus 1. I wish to prove that 2 times n sub k plus 1 and 2 times n sub k plus 1 are relatively prime for all but finitely many positive integers k. And so where do we want to start? We're given this sort of recurrence relationship, right? So we'd like to analyze this a bit more. And so how do we get from n sub k minus 1 and n sub k minus 1 to n sub k and n sub k? Well, for both of them, we double it, and then we increment by 1, and then we take we divide both of them and make them relatively prime. And to make them relatively prime, we can take the greatest common divisor of both of them and just divide it, right? And so we want to write that out explicitly. So if we let g sub k be the greatest common divisor of 2 times n sub k minus 1 plus 1 and 2 times n sub k minus 1 plus 1, we can write m sub k as 2 times n sub k minus 1 plus 1 all over g sub k. And we can do that with n sub k in a similar way. And also writing out the greatest common divisor in this way, proving that 2 times n sub k plus 1 and 2 times n sub k plus 1 are relatively prime for all but finitely many positive integers k means that we'd like to show that the greatest common divisor, or g sub k, is greater than 1 for all but finitely many positive integers. Or it is 1 for all but finitely many positive integers k. So for only finitely many k, we have that g sub k is greater than 1. And so this gives us another way to prove this. And we also want to note that 2 times n sub k minus 1 plus 1 and 2 times n sub k minus 1 plus 1 are both odd. And so that means that g sub k must also be odd, right? So that will come in important later on. So note that g sub k is odd. And going back to this recurrence, the first step I said that we did was we doubled it. For each term, we doubled the previous one and then incremented by 1. And we do that for both terms. And so we can sort of identify a monovariant if we look at their difference, right? And that's where it comes from. We're doing the same to both of them. So something should stay the same in some way between their difference, right? And so in particular, when we take their difference, we have that the one incrementing by 1 will both cancel out, and then we can factor out the multiplying by 2. So let's write that out. N sub k minus n sub k. Using what we wrote out before, we have that it's equal to 2 times n sub k minus 1 plus 1 over g sub k minus 2 times n sub k minus 1 plus 1 over g sub k. This equals, combining them, we have 2 times n sub k minus 1 minus n sub k minus 1 all over g sub k. Right, and this is monovariant in a way where if we ignore dividing by this g sub k term, we have the difference is always doubling, right? And combined with the fact that g sub k is odd, right? So it can't divide a power of 2. So this motivates the idea of looking at this difference as a power of 2 times an odd integer. So if we write m sub k, let's put it over here. Let m sub k minus n sub k is equal to 2 times some power times b sub k, where b sub k odd is the odd component of the difference. Then we can immediately write the difference as 2 times, right, the previous term's difference, which using this form is 2 times a sub k minus 1 times b sub k minus 1 all over g sub k. And so if we multiply the 2 in, it will combine with this to make a power of 2, and then b sub k minus 1 remains odd, and g sub k remains odd. So we must have that g sub k divides b sub k minus 1. So writing that out is 2 times a sub k minus 1 plus 1 times b sub k minus 1 over g sub k. And so looking at how we define this difference over here, right, you can see that just matching the terms, we get that a sub k is equal to a sub k minus 1 plus 1, and b sub k is equal to b sub k minus 1 over g sub k. And remember that to show that there are only finitely many positive integer k where these are relatively prime is equivalent to showing that g sub k is greater than 1 for only finitely many k. So let's look at the sequence of b sub k's then, because that's the sequence that has a g sub k term inside it. Right? And so the sequence b sub k, we get it from the previous term dividing by g sub k. And so we immediately get that b sub k is decreasing, is a decreasing sequence of positive integers. And that's important to note, right? Because it's a decreasing sequence of positive integers, and so it can only decrease a finite number of times, right? Because it must always be greater than 1. So if we have b sub k is greater than b sub k plus 1, this can only happen for finite number of k. Finite. Because otherwise, if it decreased for an infinite number of k, then that would necessarily mean that it would decrease towards negative infinity, right? But it is a positive integer, so it can't ever be less than 1. And so note that this happens for when the divisor, so g sub k, is greater than 1. And so this implies g sub k is greater than 1 also for finite number of k. Yeah, but that's exactly what we wanted to show, right? G sub k greater than 1 for finite number of k means that the greatest common divisor of any two of these terms is greater than 1 for a finite number of k. And if it's greater than 1, that means they're not relatively prime. So for only finite number of k, these two terms are not relatively prime. And that's exactly what we wanted to show. And, right, so just writing that explicitly, g sub k is greater than 1 for a finite number of k. So greatest common divisor of 2 times n sub k plus 1 and 2 times n sub k plus 1 equals 1 for all but finite. Okay. And we're done.